Alright, so let's say you're given this situation here, and the question says, consider the situation above of a rocket traveling in space. If the rocket wants to accelerate as fast as possible between time t equals 0 and some later time t, what must be the corresponding mass of the rocket? To start, we know from the conservation of momentum that the following relationship is true, given here, where v is the velocity of the rocket, vex is the velocity of the gas expelled during the rocket's motion, m is mass of the rocket, and t is time. This equation tells us that an effective rocket will a. burn fuel at a rapid rate, which means that the negative change in the mass divided by change in time is large. So this makes sense because remember we have to note that the change in mass or change in time is negative because as rocket travels it loses mass, so the change in mass is going to be negative because remember change in mass is going to be given by this, the rocket's losing mass, so mass 2 is less than mass 1. So this means that negative change in mass over change in time is going to be positive. And if we look at this equation for the rocket's motion in space, we can see that if we have a large negative change in mass over change in time value, this will yield a large change in velocity, which means that the rocket's going to go faster. The second thing to build an effective rocket, which essentially just means to build a rocket that has a fast velocity. To yield a larger velocity, the rocket should eject fuel at a rapid rate. So if we make vex large, which is the velocity of the expelled gas, and since the change in velocity over change in time is directly proportional to the velocity of the expelled gas, if we increase the velocity of the expelled gas, we also get an increase in the change in velocity over change in time, which means that the rocket's going to go faster. And we can also remember this is linked to the acceleration. And if we take the velocity expelled as constant, we can integrate the equation as follows. We can multiply both sides by dt and then take the integral of both sides, where the bounds here, VL, MO, are the initial velocity and mass of the rocket, and then V and M are the later mass and velocity of the rocket. And so if we integrate and solve, we end up getting this relationship here. And so this is the velocity of the rocket as a function of the mass of the rocket. If we look at this term on the right here, MO divided by M, this is the original mass divided by the mass after the fuel has been exhausted. So how do we want to make this ratio to yield the largest velocity? Note that we're taking the natural logarithm of MO divided by M, and we can note that the natural log follows this general pattern here, where log x increases as x increases. Therefore, we're going to want MO divided by M to be as large as possible to yield the largest velocity value. So how do we make this as large as possible? We can do this by making the initial mass of the rocket much larger than the mass at the later time. And this is done by making the rocket's mass mostly made of fuel. So our initial mass of the rocket is going to be as large as possible, made of fuel. And then when we burn the fuel, the final mass of the rocket is going to be very small. So a very large number divided by a very small number is going to yield a very large number, like seen in this example. So when we make the natural log as large as possible, this also yields a final velocity of the rocket, which is as large as possible.